The topic of this lecture is to show that epsilon transitions in non-deterministic finite automata are not essential. They can be removed, preserving the same recognized language. And the result I want to show, theorem, I think that in your lecture notes we have it formulated as a lemma. So it says for any non-deterministic finite automaton A of the form Q sigma delta Q0 F, with delta being as usual a transition relation over sigma, but also potentially with epsilon transitions. I think that this was with parentheses. There is an equivalent NFA B, and in fact I'm going to show you that we can even keep the same states, obviously the same alphabet. We will have a different transition relation, but the initial state can stay the same, and we will have a different set of final states. But the crucial point is that delta prime is a transition relation that has no epsilon transitions. So in all the transitions we have in delta prime, we have to have letters and no epsilon on this second component. And I'm going to prove this in the following way. First, I'm going to introduce the so-called closure. So we define the closure of state P. And we define it in the following way. We say that close P is all the states from Q in such a way that you can get from P to Q with epsilon transitions in the automaton A. So if I just copy these definitions, so A was the automaton Q sigma delta Q0 F, and remember delta could have had epsilon transitions, so it's of this type. And I want to build now this automaton B, which will have the same states and the same alphabet. And here I introduce a different transition relation and a different set of final states. So the delta prime I want to build, obviously the goal is that I'm going to build it on Q times sigma times Q, so no epsilon transitions. And the way I'm going to do it is that I will say, I will have a transition PAQ in delta prime, if and only if, so that's how delta prime is defined. I have P prime A Q in delta for some P prime in the closure of P. What I mean by this is that if you had in your original automaton A, if you had something like this, that you would be reaching with one or more epsilon transitions, you would reach a state P prime, and then from P prime you would go to Q with letter A. So this would be in automaton A. And in automaton B, I would just indicate the direct transition from P to Q with letter A. And so I would argue that intuitively, that's exactly what you would like to have. From P to Q, you are reaching with letter A, going also through a number of potential epsilon transitions. And so I'm indicating this directly. You go from P to Q with letter A in B. And the other thing that I have to define is the set F prime. So F prime, the set of final states in the automaton B, is the set of all states in Q with the property that closure of Q intersected with F is different than the empty set. And so what I mean by this is that if you have a set Q and through a number of epsilon transitions you go to a state F, which happens to be a final state in automaton A, then simply I'm going to declare that Q such a Q. So the consequence is in this way. I'm going to declare that Q is a final state in the automaton B. So again, I would argue that that's exactly what you would like to have. If in here you have a longer computation that takes you to Q, and then by epsilon, the computation by an epsilon or more transitions, you end up in a final state, meaning that you have an accepting computation, then I would say that, in my new automaton, I can just stop the computation in Q and just simply declare Q as a final state in my automaton. So I would argue that intuitively I capture the same computations as in automaton A. And obviously I'm going to prove this with a formal argument in just a moment, but the intuition is here. And so the claim is that if I have this construction, the two automata are equivalent, so their languages are the same. Here is how we can prove this. If I take, if I show this inclusion first, and let me just for maybe for the clarity of the argument, I will say if I have epsilon to be in the language of A. So if it's in the language, then it means that I have an accepting computation starting from the initial state and going with some epsilon transitions to a state F so maybe I can show the whole transition. So I could go maybe to a state Q1, and then I can go to a state Q2 with epsilon transitions. But eventually, it means that I will get to some state which is a final state. And so that's everything in automaton A. So what this means is that if we have such a sequence of transitions, this means that the QM, and in fact all the other states, but I make the point about QM. QM is in a closure of Q0. And because QM is a final state, this means that in the new automaton, Q0 is going to be a final state. And so here I have in my new automaton, Q0 is an initial state, and it's also a final state. So that means automatically that the empty word is accepted by the second automaton. So now, so this is the argument for the empty word. If it happened to be in this language, then automatically it's also in this language. But now let's take another word, a non-empty word in the language of A. This is non-empty, and I'm going to take a. So what this means is that there is an accepting computation on W, and now I'm going to show this this accepting computation. Maybe I just write here the letters of W. So this is A1, A2, AM, and all these letters. So these are all letters from sigma. So my accepting computation starts for W starts from Q0, and I mean, before I read the first letter, there is a chance that I might be doing a number of epsilon transitions, And that will take me to, say, I will just write it like this. Maybe this is a state, and then with epsilon transitions, maybe I go to a number of other states. And only after that, so all of these are epsilon transitions, but at some point, eventually, I will have to read this first letter, A1, and that will take me to state Q1. And then maybe my automaton A, so these are all in automaton A. And then maybe my automaton A again has to go through a number of epsilon transitions. It doesn't have to, but maybe it does. And maybe it goes to Q1, 1, and then with epsilon transitions, it goes to Q1, 2, and so on. But eventually, so maybe this goes to this state, but eventually it's going to have to read the second state, second letter from the input, which is A2, and it goes to state Q2, and so on. So it's going to have a number of epsilon transitions, and then a transition with one of the letters from the input, and then it goes again, potentially a number of epsilon transitions, then a transition with the next letter from the input, and so on. So in the end, it reads the last letter from my input, and it goes to some state QM, and then maybe again, in the end, I have the option of going through a number of epsilon transitions, and I go to a state which is final state in automaton A. And the point here is that I can group these transitions from A. So if I take these epsilon transitions and I take it together with the first letter of first real transition with a letter in this automaton, this defines one single transition in my automaton. So this defines the transition Q0 goes with letter A1 into Q1. So this would be in automaton B. And the reason it's like that is because transitions in automaton B were defined to be anything that you can reach from one of the states in the closure of P. And that's exactly what we have in here. This state is in the closure of Q0, and with a letter A1, I go to Q1. So that means that in automaton B, I go directly from Q0 to Q1 with letter A1. And then the same thing goes for this part. I take all of these epsilon transitions and I take the next letter transition. And in automaton B, this is one single transition with letter A2, exactly this one from here. And it goes to state Q2. And it goes in the same way. In the end, what I have is all these epsilon transitions before this letter AM are taken into account into one single transition with letter AM, and that takes me to state QM. So this is in automaton B. And the point is that now we have this definition of the final states, and because we have this sequence of epsilon transitions in here, it means that really the closure of QM includes this state, and that's a final state. So it means that by definition, this is a final state in my automaton B. So in other words, what we get is that, I'm just going to write it here. I'm sorry about this writing on small spaces, but the consequence is that W is in the language of B. So that proves this inclusion we wanted to prove. And now for the other inclusion, we have the other inclusion. And again, so I will have to think about this, that if epsilon is in the language of B. Again, the automaton B doesn't have any epsilon transition, so this implies right away the only chance for epsilon to be, the empty word to be in the language is that Q0 is in F prime. Otherwise, there is no other way to go to a final state because I don't have epsilon transitions. And this is equivalent, by the way, we have defined F prime. This is equivalent with saying that the closure of Q0, and that means the closure in automaton A, intersected with F, is non-empty. So what this means is that you will have a number of epsilon transitions in A leading to a final state. And so this implies that epsilon is in the language of A because this is an accepting computation for the empty word in automaton A. And now if I take a word W in the language of B, and this is non-empty, meaning that it's made of letters, say A1, A2, and so on, AM. These are all letters. So because it's in the language, I have an accepting computation. And in this computation, all the transitions are reading one letter from the input. So I have exactly M transitions, one for each letter. So this is in automaton B. It goes to state Q1, and then it goes to state Q2, and so on. And that takes me to state QM, and this happens to be, a final state in B. So all of these transitions are in B. But now, if we remember how these transitions were defined in B, what this really means is that in automaton A, there is a number of epsilon transitions that takes me to some state, let's say Q 0I0, and then with letter A1, I go to state Q1. So all of these things, they are in automaton A. That was just the way we have defined the transitions in B. I define such a transition if there was a similar transition in A from a state that can be reached from Q0 through a number of epsilon transitions. And same argument holds for this one. Because I have this transition in B, by the way we have defined these transitions, what it means is that I have a number of epsilon transitions in A from Q1 to whatever state, let's say Q1I1. And from there, I have a transition with letter A2 in automaton A to this state Q2, and so on. So what it means is that for each single transition here, there is a number of transitions but they will anyway lead you from Q0 to Q1. So the same argument goes to the end here, and I reach QM. And all of these things, they are in automaton A. So all of this computation I'm doing is in automaton A. And then the point is that QM is in F prime, but remember F prime was defined to be all the states that have a final state in their closure. So the fact that this is in F prime, it means that in its closure, meaning in one of these states that you can reach by epsilon transitions in automaton A, one of these, for example, this one, is a final state in automaton A. And so the point here is that this, what we have defined on this part, this is now an accepting computation for W in automaton A. So obviously this implies that W is in the language of A, which proves the inclusion we wanted to prove. So this concludes our proof that indeed our construction is correct. The automaton we have built is indeed equivalent with the one that we started from, And moreover, the second one doesn't have any epsilon transitions. And that was exactly the point we wanted to make. Let me show you now an example. And I'm going to just define it both, formally and visually. So A has 5 states, 0, 1, 2, 3, 4. It has 4 letters, A, B, C, D, and it has this delta that I define in a moment. 0 is the initial state, and 3, 4 are the final states. And delta is defined through the following transitions. I'm going to show it now visually, so you can have right away an easy way of observing this. So the automaton A is going to be this one from state 0, which is in an initial state. I go with epsilon in state 1, and I go with letter A to state 2. And also from 1 to 2, I go with letter B. And now from 2, I go to state 3 with letter C. And I go with letter D into state 4. And also from 3 to 4, I go with epsilon. And from 4 to 1, I go with epsilon. So that's the whole automaton. And 3 and 4, they are final states. And I would like to propose that you pause this video now for a moment and you think about what's the language recognized by this automaton. Just describe this language for me, so that when we build our equivalent automaton, we have a way to check that indeed we have achieved our objective. So pause this video and think for a moment, what's the language recognized by this automaton? So I would argue that the language that this automaton recognizes is the following. So we have to think about all the words that are going to take us from state 0 to one of the states 3 and 4. And you see, the way this flows is that from state 0, you will eventually reach state 2 anyway, whether you reach it directly with letter A or you go through this route, first epsilon and then B, but you are going to reach state 2. And then from this state 2, you radiate to state 4, whether directly or indirectly through state 3. And then from state 4, you have a cycle back to state 2, and then this just keeps going. So in other words, what this is from state 0, you first reach state 2 with letters either A or B. And then from state 2, you reach one of the final states, 3 and 4, with either letter C going to state 3, or with letter D going to state 4. So C and D you are allowed to do, and you can also stop here, but also you can now cycle back. So from 3 you anyway go to 4, and from 4 essentially you go to state 1 with letter B. So you can have then any number of B and then either C, so BC, or BD, which will take you again to states 3 and 4. So this is going to be BC and BD, and this you can iterate as many times as you like, and maybe 0 times. Once you are in state 3 or 4, then again you go with B, and then either with C or with D into one of these states, and you just iterate. So BC or BD can have as many occurrences as you like. So I would argue that intuitively this should be quite clear to you that the language of this automaton is words that have on the first position either A or B, on the second position either C or D, and then any number of occurrences of the words BC and BD in a sequence, one after the other one. And here is how I'm now building my automaton. So I'm going to calculate the closure of the states. So the closure of state 0. So closure of state 0 is I always include 0 in the closure, and it's all the states that I can reach with epsilon from 0. So it's state 1 in this case. From 0, I just go to 1, and from 1 there is no further way with epsilon transition, so just 0 and 1. The closure of 1 is obviously 1 is always a part of this, and from 1 I cannot go anywhere further with epsilon transition, so it's just 1. And then closure of 2 is from 2, there is no epsilon transition anywhere, so it's just state 2. Closure of 3, obviously state 3 is always there, and from 3 I can go to state 4, so 4 is there, and from 4 I can continue to state 1, and from 1 I don't go any further, but so 1 is also here. And then closure of 4, again obviously 4 is in, and from 4 I can go to state 1 with epsilon transition, so 4 and 1 are in my closure. And so now I'm building my automaton B, and I'm going to build it visually in the following way. So it has the same states as before, so in particular state 0, and the initial state is the same as in A, so 0 is an initial state. And then essentially the construction is like this. I have to think about how I transition from state 0 with all these letters A, B, C, D. And the construction says, well, take all of the transitions with A, B, C, and D from these states in a closure of 0. So anything that you could leave from 0 or 1 in your original automaton, you are now going to leave from 0. So in particular, in the original automaton, I was leaving with A from 0 to 2. So I'm going to have it also here. So from 0 to 2, I go with A. And also because I was leaving from 1 to 2 with letter B, so that means that now in this automaton, I go from 0 to 2 with letter B. So again, the idea is I will have a transition from 0 to 2 with letter B simply because in the original automaton, I could go this route. So meaning that I could go to 1 in the closure, and then from 1 to 2, I would go with B. So I have a direct transition in here. And then from state 1, the idea is you look at the closure, and whatever transitions, whatever letter transitions you have from these states, you're putting them in here starting from state 1. So this is easy. I just copy this B transition that I had in the original automaton. And now from state 2, this is also easy because the closure of 2 is exactly made of state 2. So from 2 I had, so I'm looking at how do I leave from this state? Well, you're left with transition C and D, and that's exactly how you are going to leave also now. You leave with C to 3, and you leave with D to state 4. And here now is the idea. So from state 3, I'm going to have transitions with potentially A, B, C, and D. And I'm going to check all such transitions from state 3, 4, and 1 in the original automaton. So let's start from this one. From 3, I wasn't going anywhere with any letter transition. There was only an epsilon transition, and I'm ignoring that. So from state 4, there was no letter transition, so I'm ignoring that as well. But from state 1, there was a B transition to state 2. So from state 1, I have a B transition to 2. So in my automaton, I'm going to have it from state 3. I will have a B transition to state 2. And now the same thing goes for the closure of 4. So I need to consider the transitions from state 4, which means you need to consider transitions from states 4 and 1 in the original automaton, and only letter transitions. And for state 4, there was no letter transition, so this one doesn't bring anything new. But from state 1, there was this B transition to 2. So now I'm going to have from state 4 a B transition to 2. So I'm going to have this transition. And finally, the final states in B, so they were anybody who in their closure sets, they had either 3 or 4. And we are checking, and this is just this one here and this one here. So these are my final states. And I realize that this construction is a little bit tedious, but take your time with this and maybe watch this video several times, and I'm sure you are going to get it. And we will have some exercises on this construction also in the demos. So now what we realize is that for all the computations that start in 0 and have to go eventually to one of these final states, state 1 is unreachable. So in fact, I could also even think about the language of this automaton ignoring state 1, because we never reach state 1 starting from 0. And so if we think about the language of this automaton, it goes like this. So from state 0, you will have to go to state 2. There is no other way but to go to state 2. And then in state 2, essentially you have either this cycle or that cycle. And I'm going to say it in this way. From state 2, you go to a final state, either this or that, with C or with D. And once you are in these final states, you can cycle back with letter B and then again go to one of these final states. And so these cycles can be taken as many times as you like. So what this means is that you first have to go with either A or B. And then from state 2, you have to reach one of these final states with either C or D. And then you could stop here, but also once you are in here, you could cycle back with a word that starts with B and then continues with either C or D. So you could also just add this word BC or BD as many times as you like. And so you can see now that just by this intuitive calculation of the language, you can see that indeed the two automata are equivalent, which was the purpose of our construction. And you can also see that they in fact look quite different. And in particular, the B automaton has no epsilon transitions. And again, we are going to play with this in a number of exercises in your demo. So don't be worried if this construction seems to be somewhat technical and tedious.